So, welcome to the second live session of mine for the week 2 of the course Structural Dynamics CE07. In today's session, we will cover following things. First, we will just review what was covered last week, that is in week 1 of this course. Then, we will see what was taught in week 2, a brief overview just to brush up the content and get everyone on the same level. Third, additional point that I find everyone must know, which will help you in all in general understanding. Then we will see a series of three questions, each one different from the other, based on the content covered in week two and assignment two. I will first explain you the question and then step by step we will solve the question. So make sure you all have a pen and a paper beside you so that you can also solve along with me. In these questions, I have tried to cover as much content as possible, and going through them will provide you much clarity and confidence over the topic. And finally, we will look into how the theoretically the things we solve can be visualized through a MATLAB code. Just like in last session we did, I will step by step guide you how to code in MATLAB and we will see the results. So if you have access to MATLAB, just keep it open in your laptop or PC. Else, just write syntax along with me and try to replicate it later on. And if any doubts, can ask me in the next live session. So I hope everyone are clear with the instructions. If you have any doubt, you can raise hand or write your query in the chat box. I will respond as soon as I will see. So let's start. During the first week of the course structural dynamics, we learned about undamped free vibration. What this is? These are structures which are undergoing initial natural vibration without any damping. We saw several problems related to undamped free vibration in single degree of freedom system, and we also wrote a MATLAB code for the same. Given the initial condition and knowing the dynamic equilibrium equation for the single degree of freedom system, the solution of undamped freely vibrating system is given as follows that you all know by now. Okay, so in week two, and now in last week, that is in week two, we went on to learn about damped free vibration in single degree of freedom system. So these are systems under freely, or we can say natural or initially induced vibrating state with some damping associated with the system. Now, before moving ahead, it is important to understand what this damping actually means. So we know in real structures dissipate some energy while undergoing vibrating motion. So to account for this energy, uh, the most common practical method is to assume that it is due to some viscous damping force, and that is what we will see ahead through numericals. So the content covered in week 2 was divided into different modules, which are as follows. In the week 2 module 1, we read about damped free vibration and derived the dynamic equilibrium equation for it. We will review that equation ahead also once, so that going through problems is easy for all. In module 2, we read about various types of damping like critical damping, and overcritical damping. We'll see these things more clearly today in MATLAB tutorial also, so just be patient about what things are coming ahead. We also read about negative damping, material damping, structural damping, and fluid damping. In module 3, we read about logarithmic decrement. So what this is? So when a structure is vibrating and there is damping, so of course there will be some loss of energy, or we can say the amplitude of vibration will decrease with time. Now, what pattern this loss is following is what is known as logarithmic decrement, and we will see a problem of how this thing comes into importance today. So you will understand the importance of logarithmic decrement. And in the last module of week 2, we saw a derivation of dynamic equilibrium equation using energy method. So moving ahead, just to brush up things, the dynamic equilibrium equation is given as inertia force plus damping force plus stiffness force is equal to externally applied force. And when we are talking about damped free vibration, we mean that there is no external force. So P, the external force is zero, so we can rewrite the equation as follows. And the same thing can be simplified with certain assumptions into an analytical model that is shown in the right side of the figure. Now, upon solving the second equation with given initial boundary condition, we get the equation of displacement versus time as given in the equation. U of t is equal to e to the power epsilon omega n t. Omega n is the natural free frequency of the system, whole multiplied by initial displacement times cos of omega d times time plus initial velocity plus epsilon times omega n plus into initial displacement upon omega d times sine of omega d times time. Now here epsilon is the critical damping ratio, and it is given by the ratio of damping to critical damping coefficient to critical damping coefficient, and is equal to c upon 2m omega naught n. These all relations you need to remember so that you can easily solve the equation. So that's why I've summarized everything into a single slide so that you can easily relate to the relations today while solving the question. And omega d is the natural frequency of the dam structure, and it is given as omega d is equal to omega n times under root of 1 minus epsilon square. And logarithmic decrement that we talked in the last slide is equal to delta is equal to ln of u1 by u2, where u1 and u2 are the amplitudes of vibration, the consecutive amplitudes of vibration, and it can also be written as 2 pi epsilon upon under root of 1 minus epsilon square. Now how this equation can be simplified we will see later on when we will cover some problems. Now, additionally, what I wanted to tell you is that I would like to just tell you how this dynamic equilibrium equation, the first equation that we saw, can be written in a much simpler way. So it is given as u of t is equal to c times epsilon e to the power minus epsilon omega n t times cos of omega d t minus phi, where c is the amplitude of vibration of for each time period, and it is given as the square of the summation of both the coefficient associated with the cos term and the sine term. And tan phi the phase difference is given as tan phi is equal to the ratio of both the coefficient. Now why this alternate form is important, because using this one can easily see how amplitude of vibration is varying with time, and secondly it is much easier to remember and also code, that we'll see later on in the MATLAB tutorial section. So just remember this relation so that while coding you remember what we are doing. So okay, so I hope everyone are clear with the things till now. Any doubts in anything covered till now? I guess everyone are clear, so I will start ahead. Okay, so let's continue ahead. Okay, so let's start with the first question. So, question one says a vibrating system consisting of a weight of 10 Newton and a spring of stiffness equal to 20 Newton per meter is viscously damped so that the ratio of two consecutive amplitude is 1 is to 1 to 0.85. We need to determine the natural frequency of the undamped system, the logarithmic decrement, the damping ratio, the damping coefficient, and the damped natural frequency. So I will give you all 5 minutes to think about this question, and then we will move on with the solution. Just reread the question and think what all relationships we need to use in this equation in this question, and how we will solve it. Okay, so now let's start with the solution. So what are initial parameters we have given? We know the weight, we know the stiffness coefficient of the spring, and we know the amplitude of two consecutive vibration. Okay, so first of all, it is important to make the analytical model so that you have a much more clarity about what is given in this given in the question and what we need to calculate. So right now we have given the weight and the stiffness coefficient. So step one is determining the natural frequency of the undamped system. Now we know the natural frequency is given by under root of k by m, where k is the stiffness of the system and m is the mass of the system. Now, just remember what is given in the question. In the question, it is given weight. So first we need to calculate mass. So weight is equal to mg, where g is acceleration due to gravity. So m will be equal to w by g. So we need to convert the weight into mass first for getting proper calculations. So omega will be equal to under root of 20 into 9.81 upon 10. So it will come out to be 4.43 radian per second. You can also recalculate this, and I am assured that the value will be the same. So this is the natural frequency of the undamped system, which was the first part of the question. Now, second is to determine the logarithmic decrement. Now we were given the ratio of we know the amplitudes u1 and u2. So logarithmic decrement is given by delta is equal to ln of u1 by u2. Now u1 was given 1 and u2 is given 0.85. So delta will be ln of 1 upon 0.85. So it would be 0.163. So this was the second part of the question. Now, third is determining the damping ratio. Damping ratio, what it is? Delta. For this, we will use the relation. We know the logarithmic decrement, so we can say delta is equal to 2 pi epsilon upon under root of 1 minus epsilon square. Now, here comes the thing that I told you earlier, how to make assumptions. So, let us assume that damping ratio is very small, is small. When this holds true, when the damping ratio is less than 10%. So, when it is less than 10%, then generally this relationship holds, not less than 10, but when it is very small, then this relationship holds. So when we assume that the damping ratio is very small, we can say that 1 minus epsilon square will tend to 0. So we can directly write delta is equal to 2 pi epsilon. Thus epsilon will be equal to delta upon 2 pi, and on solving this we will get 0.163 upon 2 pi, which is equal to 0.026 or 2.6%. If I remember, if the damping ratio is less than 10%, then you can make this assumption of 1 minus epsilon square tends to 0, so that you can simplify the relation. So this is the third part of the question of determining the damping ratio, epsilon. Now, we know epsilon, so we need to determine the damping coefficient. So we know epsilon is equal to C upon CR, where C is the damping coefficient and CR is the critical damping coefficient. Now we know the relationship for CR, it is equal to 2m omega n, and we know the mass of the system and also the natural frequency of the system. But still, we can simplify m omega n into under root of km, because omega n is equal to under root of k by m. So m into under root of k by m will be equal to under root of k times m. So C will be equal to epsilon into 2 into under root of k by m. We know the value of epsilon, we calculated in step 3. We know the value of k and we know the value of m. M is weight upon acceleration due to gravity. So substituting all the values, we will get c is equal to under root 0.026 times 2 times under root of 20 into 10 upon 9.81. So it will come out to be 0.235 newton second per meter. Always remember the units, because if you will place all the values in proper units, then you will get a proper unit in the outcome also. So please make sure that you are converting the units properly and you remember what is the outcome. So step 4 was determining the damping coefficient that we have determined. And finally, step 5 was to determine the damped natural frequency, omega d. So we know omega n, we know the damping ratio. So omega d is given as omega n times under root of 1 minus epsilon square. Here we don't need to assume the damping issue to be small. I mistakenly wrote that. You can directly put the omega n and the epsilon value, and you will observe that omega d is equal to 4.43 times 1 minus 0.026 square, which is equal to 4.428 radian per second. Now you see, when the damping ratio is very small, omega d is much more closer to omega n. That's why we make assumption of 1 minus epsilon square tends to 0 while simplifying other relationships. So in this way, we estimated all the five parameters that we were talking about. We calculated the natural frequency of undamped system. We calculated the logarithmic decrement. We estimated what is damping ratio, the damping coefficient, and the damped natural frequency. So through this question, we saw how different parameters that are not initially defined in the system can be easily calculated. Now, in the same way, you can see n number of questions where just the values will be represented in a different way, and you need to calculate the remaining values. So just remember all the relationships properly. Make sure that you are assuming things properly and converting units properly. And if you remember relation, then make sure of all the things. The calculation is very easy. That can be seen through this question. I hope everyone are clear with the question. Any doubts in this question? Any relationship that you didn't understood, or anything that was wrong you feel? Okay, so let's see the next question now. So this is question 2. A platform of weight W is equal to 20 Newton. It's been supported by four equal columns that are clamped to the foundation as well as to the platform. Experimentally, it has been determined that a static force of zero point 0.5 Newton applied horizontally to the platform produces a displacement of delta is equal to 10 centimeter. It is estimated that damping in the structure is of order of 5% of the critical damping. Determine for this structure the following: undamped natural frequency, absolute damping coefficient, logarithmic decrement, the number of cycles, and the time required for the amplitude of motion to be reduced from the initial value of 10 centimeter to 1 centimeter. So again, you can see in this question some of the values are given, some of the values we need to calculate, and the main part is the fourth part where we need to the first three we saw in the last question also, but here the new point come is the fourth point that we need to see how we calculate. So I will give you a couple of minutes to think about the question, the values that has been given, and then we will see the solution. Try to solve the question by yourself first, and then we will see the solution. Yes, there's some. We will see the solution. You can do your calculation by at your end, and we will see what values comes. Okay, so let's see the solution now. In the question, we know the weight of this platform. We know a force was applied of zero point 0.5 Newton, which produced the displacement of 10 centimeter, and we know the damping ratio of 5 was 5%. So let's see the solution, solution of this question step by step. So again, first we need to draw the analytical model. So in this model, we know a force was applied, weight we know, we need to, but we don't know the stiffness of the spring, and we don't know the damping coefficient. So first step was to determine the undamped natural frequency, but for that we need to estimate the stiffness. So how we know the undamped natural frequency is given by under root of k by m, and we need to calculate the stiffness first. And but we know an external force and how much displacement it produce. So we know force is equal to k times delta. So k can be written as p upon delta. P is 5.5 Newton, I guess. P is 5, point 0.5 Newton. Just make the correction in the analytical model, and delta is 10 centimeter, which can be written as 100 mm. So k will come out to be 0.005 Newton per mm, or we can write it as 5 Newton per meter. Now we know the value of k, and we know the mass. Mass will be given by W by G. W is 20 and G is equal to 9.81. So the undamped natural frequency of the system will be under root of K by M, which will come out to be 5 times 9.81 upon 20. So it will be equal to approximately equal to 1.57 radian per second. So one of you calculated it correctly. It was 1.57 radian per second. Now we know the value of K, and we know the undamped natural frequency of the system. Second is to calculate the absolute damping coefficient. So for that we need to know the critical damping coefficient also. But since we know the value of m and k, we can use this relationship directly. C is equal to epsilon times CR, which is equal to epsilon times 2m omega n, and m omega n, as done in the previous question, can be simplified into under root of k times m. So the absolute damping coefficient will be value of epsilon is given, the ratio of damping coefficients, it was given 5%. So it is 0.05 times 2 times 5 into 20 by 9.81. So it is equal to 0.139 Newton second per meter. So this is the absolute damping coefficient. Third is the logarithmic decrement. Now we here we don't know the ratio of amplitudes. of successive peaks. So what we will use? We will use the other relation, 2 pi epsilon upon under root of 1 minus epsilon square. But since the value of epsilon is less than 10%, so we can directly assume that 1 minus epsilon square is almost equal to 0. So we can directly use the relation delta is equal to 2 pi epsilon. So we know the value of epsilon, so delta will be 2 pi times 0.5, 0.05. So it will be 0.11314. And then using this relationship, we can also estimate the amplitude, the ratio of amplitudes as ln u1 by u2 or u0 by u1. You can write anything. Is it should be just be successive peaks. So u1 by u2 is also correct, u2 by u3 is also correct, u0 by u1 is also correct. So u0 by u1 will be e to the power, if I take if I remove ln, we will place e on the opposite side, so it will be e to the power 0.13314, so it will be equal to 1.37. But the thing that we need to calculate in this question was logarithmic decrement, that is delta is equal to 0.314. So just remember that value. Now we have estimated all the basic parameters of the system. So we will move on with the final part of the question, that was determining the number of cycles and the time required for the amplitude of motion to reduce from the initial value of 10 centimeter to 1 centimeter. Now how this will happen, because there is damping in the system, so slowly the amplitude will reduce, but we don't know in how many number of cycle and how much time it will take for the amplitude to reduce. So first we'll calculate the number of cycle. Now we know the ratio of ratio between the first amplitude and the second amplitude, but we don't know how many cycles it is going through. So the ratio between the first amplitude u0 and the amplitude, say after k cycles, is uk, may be expressed as u0 by uk is equal to u0 by u1 into u1 by u2 into u2 by u3 times uk minus 1 by uk. If you will simplify the RHS side, it will be u0 by uk only. We have just broken it up into successive cycles, so that we can see the solution. Now take ln on both the side. So what you will get, ln u0 by uk is equal to ln u0 by u1 plus ln u1 by u2 plus ln u2 by u3. Now the ratio of successive peaks is ln of ratio of successive peaks is known as logarithmic decrement. So everything on the RHS side is delta only. So ln u0 by uk will come out to be k times delta. Now we know u naught, that is our initial value, which is 10 centimeter, and we know uk, which is 1 centimeter, that is the final amplitude that we want. So and we know the value of logarithmic decrement, that is after each cycle how much there is decrement in amplitude. So ln 10 by 1 is equal to k times 0.134 0.1314. So in solving this, we will get k is equal to 7.73, or we can say approximately 8 cycles. So using this, we got to know how many cycle it will take for the initial value of amplitude to reduce from 10 to 1 centimeter. I hope this relationship is clear, and all the thing that we did in this part of the question is clear. How we took log on both the side, and log of xy is equal to log of x plus log of y. I hope everyone knows this mathematical property, and you know the definition of logarithmic decrement. So how we wrote delta for each logs on the for each ln on the right hand side. So first part of the step 4 is done, calculating the done number of cycles. Now second is to calculate the time required. But for this, first we need to know the time period of one cycle. We know the natural frequency of the system, and we know the epsilon. So damped natural frequency will be equal to omega n times under root of 1 minus epsilon square. Omega n value will calculate it in the step 1, and epsilon we knew from the question. So omega d will be 1.57 times 1 minus 0.05 square under root of 1 minus 0.05 square. So it will come out to be 1.568 radian per second. And now, since we know the value of omega d, we can calculate the time period of damped motion, of damped vibration, which will be equal to 2 pi upon omega d. And on substituting the value, you will get it at approximately 4 seconds, 2 into pi upon 1.568. But This is for one cycle. We know from the first part of this step 4 that how many cycle it took for the amplitude to reduce from 10 to 1 centimeter. It took 8 cycles. So the total time for 8 cycle will be 32 seconds. So it will take 32 seconds for the amplitude to reduce from 10 centimeter to 1 centimeter in 8 cycles. And it will take 8 cycles for this to complete. So in this way, we saw all the parts of the second question. We first saw what all initial parameters are given, how these initial parameters can help us to calculate other required parameters, and finally how we can reduce it to calculate much more complicated thing of the system. So this was all about question 2. I hope this question is clear to everyone. Any doubts in the question? In the last part of the question, especially? Okay, so let's see the third question now. This is the final question of today's tutorial. After this, we'll move on to the MATLAB part. So, question 3 is a machine weighing 10 Newton is mounted through springs having a total stiffness of K is equal to 2000 Newton per meter to a simply supported beam as shown in the figure. Determine using analytical model the equivalent mass, the equivalent spring constant, and the equivalent damping coefficient for the system. Assume to have 10% of critical damping, neglect the mass of the beam. And in the question, it is given EI is equal to, for the beam, EI is equal to 10 to the power 4 Newton per meter, and length of the beam is 20 meter. So I will again give you couple of minutes to think about what all is given in the question and how we can solve this question. And then we will see step by step how we can determine all the values. Just a hint in this question, in the last week, I told you one relationship about in an additional learning part that will be used. So think about what you need to calculate first. We'll see the solution in a couple of minutes. Okay, so let's see the solution of this question. We know the initial parameters: weight of the machine 10 Newton. The stiffness of the spring is K is equal to 2000 Newton per meter, and the critical damping is 10%. The damping ratio is 10%. It is given, is assumed to have 10% of the critical damping. So it means that 10% is the damping ratio. Okay, and we can neglect the mass of the beam. So the total mass will be just the mass of the machine. So equivalent mass you can directly say it is due to the weighing machine only. But the equivalent spring constant will be different. It is not just 2000 Newton per meter. So first step is to determine the equivalent spring constant of the system. Again, first draw the analytical model so that you have much more clarity about what is there in the question and what we need to calculate. So the spring constant Kb for the uniform simply supported beam with the weight in the center can be obtained from the relationship if we say deflection delta has been there due to a force P applied at the center of beam, then we know the relationship delta is equal to PL cube upon 48 EI. These relationship you must know as a prerequisite of this course. So if you know delta, we can say the stiffness of the beam is P upon delta, which is 48 EI by L cube. Now the value of EI was given in the question as 10 to the power 4 and the length of the beam is 20 meter. So it will be 48 into 10 to the power 4 upon 20 cube, which is equal to 60 Newton per meter. So this is the stiffness coefficient of the beam. And we also know the stiffness coefficient of the spring. And both these things are in series. You can visualize these from the question. The both the spring and the beam are in series. So the equivalent spring constant will be calculated as 1 upon k is equal to 1 upon k plus 1 upon kb. We saw these relationship about the springs in series and springs in parallel in the last week tutorial also. So if anyone don't know about these equivalent relationship, can review that tutorial again. So 1 upon Ke will be equal to 1 upon 2000. 2000 was given, that is the stiffness coefficient of the spring, and plus 1 upon Kb, that is 1 upon 60 that we calculated right now for the beam, the stiffness coefficient of the beam. So Ke, after calculation, you will get K is equal to 58.25 Newton per meter. So this is the equivalent spring constant. Step 2 is to determine the equivalent mass of the system. Now it was given in the question that we can neglect the weight of the beam. So the equivalent mass will be just the mass of the weighing machine that was put in addition to the on the beam, which is mass will be equal to W by G. W was given 10 Newton, so it will be equal to W upon 9.81, which is equivalent to 1.019 kg. So this is the equivalent mass of the system. Now we know the equivalent mass, we know the equivalent spring constant. So equivalent damping coefficient, again we can use the relationship C upon Ce upon Cr is equal to epsilon. We first need to determine critical damping coefficient, which can be given as 2m omega n. Again, m omega n can be written as under root of km. So it will be 2 times under root of 58.25 into 1.019. So it will be 16.02 Newton second per meter. This is the uh, critical damping coefficient. So absolute damping coefficient will be epsilon times Cr. Epsilon was given 10% of the critical damping. So it will be zero point 0.1 times 16.02. So it will be 1.062 Newton second per meter. So was the third and the final part of the question. So in this way, we calculated the equivalent spring constant. We determined the equivalent mass of the system, which was just to confuse you. It was simply the weight of the weighing balance, the weighing machine, and then we calculated the equivalent damping coefficient. I hope this question is clear to everyone. This question was much more related to what we saw in the week one tutorial, so that you can relate things properly. Any doubts in this question? Any doubts to anyone? I hope this question is clear, so we will proceed ahead now.
Sir,
Yeah, say.
railing method is different, or I want to know about some about railing method.
Can you please write your doubt in the chat box? Your voice is not clear to me.
Okay, okay, sir.
Relay method to find out fundamental frequency. Yeah, so what is the doubt in this thing?
Sir, this is a different method.
Yeah, it may be a different method. What, like, is it related to this question or something else?
Something else. University exam related. This question is uh, uh, in a question about solve railing method. Fundamental frequency using railing method. In syllabus, there is a railing method. In future, uh,
Okay.
यानी
I
फ्यूचर में सिलेबस में है अपने या फिर कुछ ऐसा पॉइंट.
that I need to see actually. If you have a doubt regarding this method, I will get back to you about this in the next class. But in the week two of the course, it was not there, so I can't say
Okay,
much about this right now.
okay, sir. Okay, thank you, sir.
If you have any doubt, I will get back to you regarding this in the next class.
Okay,
Okay?
okay, sir.
Yeah. So I hope these three questions are clear to everyone. Now we will see the MATLAB tutorial part. As a part of additional learning, in every live session of mine, I will cover a tutorial on MATLAB, wherein I will describe a single degree of freedom system covered in the week content. So for week two, we will see how displacement response of an undamped free vibration single degree of freedom system is represented in a MATLAB. So let's see. Our objective is to visualize the motion of a single simple damped oscillatory model with the single degree of freedom system. And for this, we will use the values that we found in question one. So remember what all values we calculated in question one, and we need to plot the response with different damping ratios now. We'll use damping ratio of 0.01. Apart instead of 0.03, we'll use the damping ratio that we calculated in question one, zero point 0.5 and zero point 0.9, and we are given the initial condition as displacement is 1 mm and velocity is zero point 0.5 mm per second. So I will open my MATLAB software in the laptop. You can see how to code as of now and implement the same later on. We'll go step by step and define everything properly and clearly. All the syntax that I will be using today are a little complex than the last time. So please pay attention. I will try to clarify all of them with time. So you don't need to worry about anything if you don't have prior experience about coding in MATLAB. But just see and learn what I am doing. So first remember all the values that we got in question one. we calculated the natural frequency. We will calculate it again, you don't need to worry. You just remember these value. The weight was 10 Newton, stiffness coefficient it was given, and we'll see the calculations. Okay, so I will be opening my MATLAB now. If you guys have MATLAB software, you can also open it. We will start in a couple of minutes. I'm waiting if any one of you wants to also code side by side, and if he or she is opening a MATLAB software in their PC or laptop. Sorry. Okay, so let's start with the question. So first, we will define the given values. Okay. So what all values are given to us? Mass m, which is 10 was the weight of the system. So mass will be 10 upon 9.81. So this I am defining as m. K was given as 20 Newton per meter. And the value of C we calculated as 0.235. If anyone remembers, this was the value of C we calculated in step 4. This was the value of C, 0.235 Newton second per meter. Okay, so these three value we obtained. Now, what are the initial conditions? So initial condition U naught, initial displacement was 1 mm, and V naught, initial velocity was zero point 0.5 mm per second. So these were the initial conditions. You can see in the right side of the workspace, all the parameters that I am defining are listed. So you can cross check also what all values you are getting. Now, we will first calculate the undamped natural frequency. This calculation we did in the question one also, but I will just again do the calculation. Omega, we will define undamped natural frequency by omega. So omega is square root of k by m. In this way, you will also learn how to use different commands in MATLAB. So for square root, we use sqrt. So sqrt of k by m. So you can see the value of omega is 4.4294. This was what we calculated. Now, critical damping coefficient. We will define it by CCR, C critical, which will be equal to 2m omega n. And m omega n can be written as under root of km. So it will be 2 times square root of k times m. So this is critical damping coefficient. And absolute, this is critical damping coefficient, and the damping ratio I'm saying defining it by xi will be equal to c upon ccr. Okay, so you can see the damping coefficient is also getting calculated as 0.026. Okay, now we were given in the question we need to take four values of damping coefficient. One we calculated and three were zero point zero 0.01. This was what we calculated, 0.5 and zero point 0.9. Now, taking different damping ratio, it will help us to visualize how the displacement response changes with the damping ratios. Okay, so now we will create a matrix. We need four damping ratios now. So, defining damping ratios now. For this, I am defining damping ratio with zeta, which will be equal to 0.01. First was that. second is xi that we calculated earlier, third is zero point 0.5, fourth is zero point 0.9. So in this way I've defined all the four damping ratios. Okay, just see the syntax of how we define things. Okay, so this is a list kind of thing where I have defined four values. It will create a matrix. Okay, you can see on the right hand side, zeta is a list or a matrix, you can say. Okay, now we have defined all the parameters that were given in the question and what we needed for calculation of. Okay, so now we'll proceed with the estimation part. Estimation is how the displacement response will change with time. Okay, now just to simplify the code, we won't write all the things again and again for different damping ratio. So we use a for loop. So for I equal to 1 to 4, since we have four damping ratios, so that's why I'm making four loops. So what this loop will do, it will run the same code four times. Okay. So for I is equal to 1 to 4, first we will define the damped natural frequency omega d. Omega we know, I'm calculating omega d will be equal to omega times square root of 1 minus epsilon square. So sqrt times 1 minus, now I have four values of epsilon. I defined it by zeta. Okay. So I will take one value at a time. How to take this value? This is the syntax. So what zeta bracket colon comma I will do, it will take one value of zeta from the list and it will calculate omega d for the same time square. So this is how we define omega d for each zeta. Okay. Now we need to plot displacement response. So we need to have a x-axis which is time. So in last tutorial we saw how we can define a timestamp. Okay, so timestamp I will define 0, 0.1 till 6. So it will be a time from 0 to 6 second with the interval of 0.1. So it will be like 0, 0.1, 0.2, 0.3 till 6. So around 600 data points this timestamp will have. This was what I taught you in the last lecture also. Okay. Now we have defined all the parameters, all the conditions. Now how we write the displacement response. So today in the additional learning part, I showed you what is the simplest way, a simple way to write the displacement response. It is given as u of t is equal to c times e to the power minus epsilon omega n t times cos of omega dt minus phi. And now in this, we need to first calculate c and phi, and also this term e to the power minus epsilon omega n t. So we will first define all these three values and then we will write this equation. Okay, so just remember this equation. So first is this value. I'm saying this is argument. Okay. So argument one, you can say any name to the parameter. So what is the that is e to the power minus epsilon omega n t. So exponential of minus epsilon, that is my zeta. I will take one value at a time. So again zeta comma I to take one value at a time times omega n. Omega n we know, initially we have estimated that thing, times time. So time we have defined t is equal to 0 to till 6 with a zero point 0.1 interval. Okay, so this is how we determine the first parameter. Second is c. What is c? C is amplitude of vibration. That is given by under root of u naught square plus v naught plus epsilon into omega n into u naught upon omega d square. So let's define this. Now remember all the brackets and all properly so that there is no mistake in the syntax. The square root of first e of 0 plus first will be u naught square. Okay, u of 0 square plus second part is v of 0 plus u of 0. Any doubts? Okay, okay, someone joined again. Okay, so where was I? Defining that amplitude c. So v of 0 plus u of 0 times Epsilon again I will define using the syntax 0 comma I, just to take one value at a time, times omega n. So omega n we defined by omega upon omega d. Okay, so this all is in second bracket, square of this. Okay, just recheck, square root of u naught square plus whole of v naught plus u naught times epsilon into omega upon omega d square. I hope this relationship is correct. We will recheck from here. So u naught square yeah, omega d square. Okay, so this relationship is correct. This is the value of c. And third, we need to calculate phi. So tan phi we know. So phi will be tan inverse. So how we write tan inverse? A tan is the code for writing tan inverse. So tan inverse of what was the value? V naught plus epsilon omega n u naught upon u naught into omega d. So it will be again p of 0 plus u of 0 times zeta semicolon comma I times omega whole upon omega d times u of 0. Okay, just check the bracket once for to assure that everything is in proper place. Okay, all the brackets are proper, everything is proper. Okay, so this is phi. Now this part is a constant. Okay, so I will define club both these into a parameter known as max, which define the maximum amplitude of each cycle, and it will be given by C dot star times arc1. Why we are doing dot star here? It is just how we multiply matrix. If you will if you know about vectors and scalars, then you will know about why I'm doing dot star. So just clarify matrix multiplication at your end so that you are clear with the syntax here. Okay, and now since we have estimated all the parameters, we can define u of for each damping ratio. What is the displacement? We can define with the relationship that we saw, c into arg1 into cos of omega times t minus phi. So this was the relationship that we had. U of t is equal to c into e to the power minus epsilon omega and t times cos of omega d t minus phi. So omega d, okay, we wrote omega dt minus phi. And now we have defined everything, so we can end the for loop. As soon as you will end the for loop, if your all syntax is correct, there will be no error, and you can see here on the right hand side all the matrix. So 61 points and everything. Okay, how the values are varying. So we took point 0.1 interval. Now, if you would have taken 0.01, then it will be 600 points. If you would have taken 1, then it would be of 6 points. So in this way, you can see all the parameters how they are defined properly. Okay, now we'll see how to plot. Okay, once we have defined everything, we need to create plot so that we can visually see what has happened. So create plot is our next step. Now we have four plots here. For four zeta values, I will have four displacement. You can see the displacement matrix is 61 cross 4. So there are four different sets of values. Now, how to represent this thing in a single figure? So for this, we will use a command known as subplot. So since I have four plots, I will define subplot as 2 comma 2. So it will create a 2 cross 2 matrix. So my figure will be divided into four parts, two rows and two columns. So in the first part of these four, I will define my first subplot as plot t comma u of. Okay, so this will define my first displacement that is associated with this value. Okay, so plot x comma y. See this at plot x comma y. So x is my fixed and y will be varying. So right now I took u of 1. Next time I will took u of 2, then u of 3, then u of 4. So 1, 2, 3, and 4. In this way we'll plot all the four displacement time curves. Okay. So this is the plot. I will give the title to this as xi is equal to 0.01. I will label the x-axis as time in seconds. Y label will be displacement in mm. Okay, so this completes my first part of the figure. You can see here the first, uh, the figure is divided into four part and we have plotted the first. Now we'll see the second, third, and fourth. Okay, so just simply press the up arrow of your keyboard and you can just go on with simply do the changes. So subplot 2 comma 2 comma 2, so it will be the second unit. So in second unit we need the second displacement time curve. So I will just change 1 to 2. Max label will be xi will be this time equal to, so this time xi is what we defined. Okay, we calculated. Okay, it was not a fixed value, so we need to define it properly. So xi will be, I defined a number and want string as an output. So this is a syntax that we use. Okay, you will learn this slowly, slowly. Just remember what I am using and what is the outcome of it, and then see on your own how to use it more properly. Okay, I did some mistake. Yeah, I will again write that thing. I used 2 equal to, that was incorrect. So title, yeah, now it is correct. X label will be time, Y label will be displacement. Okay, now you see the figure. You can see for xi is equal to 0.03 how the curve is shaping. So you can see the displacement profile is decreasing at a much larger rate when the damping ratio is increasing. Now similarly we'll do for the other two. Subplot 2 comma 2 comma 3. For this we'll have plot u of 3. Xi will be this time equal to zero point 0.5. X label will be time, Y label will be displacement, and finally the final plot. Xi is zero point 0.9, X is defined, Y label. So in this way we have defined all the plots. Now see the figure. So you can see as the damping ratio is increasing, how the displacement profile is changing. When the damping ratio is very small, you can see that rate at which the amplitude of displacement is decreasing is also very small. But as the damping ratio is increasing, you can see how strongly the amplitude of vibration is decreasing. Okay, so in this way, you can visually see what is the effect of damping on a structure through MATLAB coding. These things you can also use solve numerically, but things are not very much clear when we do numerically. Through MATLAB code, you can much more visually see what is happening. Any doubts in this code, what I wrote? I hope everyone were able to follow what I was writing. If this is your first time in MATLAB, then you will find it a bit tricky, but I have attached the same uh, coding structure in the slide also, so you can also try it later on by your own, and you will get much more clarity. Now you can also try the same thing for undercritical, critical, and overcritical damping. Just use the same question and took three damping values, that three damping ratio. Take one as zero point 0.1, 1, and 2, and see what is the response, displacement or time response. So you will be able to visually see what is the effect of type of damping on the system. Okay, try to do these things on your own so that you understand it better. I've told you, I have taught you the basics of how to write in MATLAB. Now you can go on with the advanced form of it. This was all for today. If anyone has any doubt, they can ask. I'm here in the meet till 8. So this was the code and this was the result. Yeah, Arshad. I guess NPTEL must have provided you, but still. This is my email. If you have any doubts, you can ask me directly also. Any doubt in the MATLAB section of today's?